Greetings. This video will cover the material for Lecture 5, which was scheduled on the 27th of January. Please make sure that you watch the entire video, be comfortable with the topics, because we will use these topics for the next few lessons, and these are some of the important points. So in Lecture 5, we are going to talk about valence electrons, LDS, which stands for Lewis dot structures, and chemical bonds. So just to go for a recap from what we did in the last week, we looked at the electronic configuration, we looked at periodic table trends, especially electronegativity and atomic radius. And if you remember, the electronegativity increases from left corner to the rightmost corner. So that's electronegativity. Whereas the atomic radius has the opposite trend in that it decreases from the right top to the left bottom. So radius here, sorry. And today we're going to look at a little more into the electrons, specifically valence electrons, and how these valence electrons are involved in bonding between atoms. So just to work on a few more examples on these arrangement of electrons, which is called as the electron configuration, I have some of these examples here. So it gives us good practice as to how to come up with the electronic configuration by looking at the element on the periodic table. So here we have hydrogen. Hydrogen is the number of electrons. The atomic number is the same as the number of electrons. So hydrogen has only one electron, so we start with 1s1 right here. So it will be 1s1 for hydrogen. Now lithium has 3 electrons, so which means we start with the first shell. The first shell has only s electrons, shell number 1. So shell number 2 will be these 2, shell number 3 will be these 3, and shell number 4 will have 4 of these. So we have already finished 2 electrons, so shell 1 has only 2 electrons max, and that is done. And going on to shell 2, we have 2s1 here because we only need to put space for one more electron, and that's how we put it into 2s1. Now if you move on to the third element in the same column, which is going to be shell number 3, so you can see that we have the first shell complete, second shell, which is S and P, 2s2 and 2p6 complete. And in the third shell, we start with the S, and there is only one more electron because these will be 10 electrons right there. So we'll have to include one electron in the 3s orbital for us to account for all the 11 electrons on the element. So I hope you guys are very comfortable with this way of writing the electronic configuration and being comfortable looking at how they get filled up as we go through the columns and the rows on the periodic table. So make sure that you look at this one clearly and be comfortable about how to put the electrons in the different shells and the different orbitals. So what I had shown previously that in the previous slide was that hydrogen has a 1s1, lithium has 1s2, 2s1, sodium has 1s2, 2s2, 2p6, and 3s1. So I have highlighted the highest number in each of these electronic configurations. These highest number, these are the outermost shells. So the outermost shells are called as valence shells. So if you if you know about curtains or something, what we have on the outermost of the curtains is a valence, like decoration. So this is where it comes from. Our outermost is always something referred to as valence. So here there is only one shell, and that becomes the outermost shell, and we have one electron right there, and we have shown it in this representation. You have only shell number 1, and shell number 1 has orbitals which can host 2 electrons. There are 2 rooms for the electrons. But since we have only 1 electron, only one of them is occupied and the other one is going to be empty. Now if you look at lithium, lithium has 1s2 and 2s1. So the first shell has 2 electrons, that is complete. The second shell has 1 electron, even though the capacity is total 8 electrons, the others will be empty once the first electron is there. The rest of it is going to be empty in that. Now if you get to sodium, we have the first shell complete, the second shell is also complete, and we are getting into the third shell here. So the first shell has 2 electrons, those are right here on the first ring, and together we have 8 electrons in the second shell. So 2 in the S and 6 in the P in the blue right here. So these are S electrons, these are the P electrons, P1, P2, P3, P4, P5 and 6. And in the third shell, that is the third ring, you only have 1 S electron. And even though you have more orbitals, they're all empty because we do not have that many electrons in sodium. So these outermost shells are called as valence shells, and these electrons are arranged in those shells around these nucleus. So I highlighted these highest numbers, and as I mentioned, these are valence shells. And the electrons in these valence shells are called as valence electrons. So if you look at each of these elements and we want to figure out the number of valence electrons here, so shell number 1 is the outermost here and it has only 1 valence electron, so this will be 1. So in case of lithium, we have 2s, 2 is the outermost and there is only 1 electron there, so that will also have 1 valence electron. When you get to sodium, it has 3s as the outermost, 3 as the outermost shell, and in the 3s orbital we have only 1 electron. This will also be 1. So you can see that each of these have 1 valence electron, which is why they are all in group 1. Feel free to use my office hours or ask me in the class. Very likely other students will probably want to work on this as well. So for nitrogen here, you can see that we have 7 as the atomic number, so which means 7 electrons. And if I write the electronic configuration here, you can see that I have 1s2, 2s2, 2p3. So the first shell is going to be complete. The second shell is the valence shell here. So the total number of electrons in all the orbitals in the outermost shell, that will become the valence electrons. So here this will be 2 plus 3, that will be 5 valence electrons. Now in case of oxygen, we have 2s, 2s2 and 2p4. So together this will be 2 plus 4, that will be 6 valence electrons. And in case of fluorine, we have these again 2 plus 5 because these are all in sequence. So this will be 7 valence electrons. And in case of neon, you can see that 2 plus 6. So that means 8. So this is where we have the octet complete. And that's why neon becomes a noble gas. So we figured out that these were the valence electrons by looking at the electronic configuration. But you can also figure it out on the periodic table. You don't have to do the electronic configuration because the way the elements are arranged on the periodic table is according to their valence electrons in their groups. So group number 1 will have 1 valence electron. Group number 2 will have 2 valence electrons. And these are the 3A. So 3, 4, 5, 6, 7. You can see that nitrogen here has 5. Oxygen here has 6 and fluorine has 7 right there, and neon is going to be right at the end. So if you look at the periodic table, you will be able to figure out the number of valence electrons. So if I were to ask you what is the valence electrons in case of gallium, you can look at the group number and this has 3 valence electrons. If I ask you what is the number of valence electrons in iodine, because it's in group 7A, So that means 7 valence electrons, and so on and so forth. So this is the reason why you want to be very comfortable looking at the periodic table, because it gives you all this information without having to write the complete electronic configuration right there. Now these valence electrons are, when we represent these valence electrons around the element, we call that as the Lewis dot structure. So for example, in case of nitrogen, we have 5 valence electrons. So you will write the symbol and then show the 5 electrons around it in that. In any order, it's okay. You don't have to write it in a legible, but as long as you show 5 dots, which represent the 5 valence electrons, and the correct symbol for the element here, which is nitrogen N, that's all it matters. Now, how would you write for oxygen? So oxygen has 6 valence electrons. So you write down oxygen in the center, and we have 2, 4, and 6 electrons. It doesn't matter which side you write or whether you write them in pairs. But because it makes sense to write them in pairs, like how we see electrons paired up, it's usually represented in this way. So if you can replicate it in this way, well and good, but don't get too worked up if you represent it in a slightly different order. But it has to be the correct number of electrons. That's more important. So we'll do a little more practice here. So take a pause here. Try to see if you can come up with the Lewis dot structure for chlorine. So chlorine atomic number is 17, so which means located on the periodic table. So chlorine 17 is going to be right here. And if I look at the number here, so 3, 4, 5, 6, 7. So chlorine will have 7 valence electrons. So which means you can write chlorine in the center and represent 7 electrons around it in this order. Another example here, calcium. Go ahead and write down the Lewis dot structure for calcium. First, identify where it is located using the atomic number. And then count the number of rows and figure out the row number, count the number of column, and look at the column number for calcium, and that will tell you the number of valence electrons. Write the element in the center and show the electrons around it. So calcium is 20 here. So 20 meaning it'll go to this place here. Remember, it's always arranged in increasing orders from first all the way to 118. So if you track the number here, that'll be on the 4th row. So now if you look at the column number here, column number will be 2. That means calcium has 2 valence electrons. You show calcium in the center and 2 valence electrons like that. So pick any element and try to come up with its electronic configuration, figure out the number of valence electrons, and also number of, write down the electronic configuration by looking at the periodic table and trying to deduce the arrangement right there. Now, why am I talking so much about valence electrons? Is because valence electrons are the ones that are involved in bonding. So when an atom A, let's say we have an atom A, generic atom A, reacts with an atom B. So there is another atom B here. So let's say the B has 2 shells or 3 shells here, and then A has 2 shells here. So let's say, for example, the A has 1 valence electron, and let's show that B has 7 valence electrons in its outermost shell. So when we say that, like I've shown the structure of Paxlovid, which is the drug that is used for COVID these days. You can see that it has a huge structure, and we have many atoms here, carbon, hydrogen, then we have the oxygens here, and there's a nitrogen here. So all of them are arranged like in a specific order, and they're bonded to each other with those bonds. So how do these bonds form is because of the interaction of the valence electrons. So when you think of these two interacting, like if I say A interacts with B, it's the valence electrons that are interacting between the two. So here, when they interact, the valence electrons here are the ones that are going to either get shared or get transferred between the atoms. So when that happens, A and B form a bond, and we show it with that line indicating that they have a bond formed between them. Now the types of chemical bonds that we normally see can be categorized into three categories here. One is called as ionic bonding. As the name suggests, it is between ions. So we have a positive ion and a negatively charged ion, and this is the bond that is formed here. This is going to be the ionic bond. Now covalent bonding, as the name suggests, they're both going to meaning share. So meaning co-opt or co-share. So when you have covalent bonding, so they share the electrons. So when you have an atom A and atom B, we show that these two electrons right here are being shared by the two atoms. So this is a covalent bond. Now metallic bond is formed when you have two metals that are right next to each other, mainly because there's not much of like sharing or transfer of electrons. It is just that the metals end up forming like very close knit interactions, and these electrons will be sort of forming a bed of electrons on that. So when one metal interacts with another metal, they end up just being right next to each other in the atomic state, but just that their electrons are free to move from one to the next. That's it. So just to give you an idea here, so ionic bond, for example, we have sodium ion, which is sodium plus, interacting with a chloride ion. So if you look at these ones here, so we can have sodium will be these ones here. This will be the chloride ion. So all of these are chloride ions, and each chloride ion and each sodium ion interact with multiple opposite charges right there. And you can see here, this is a covalent bond. So this is like, let's say, hydrogen and chlorine that form a bond here. So hydrogen and chlorine, they form a bond. So here, this is metal. You can see that we have this sort of a blurred image, or just trying to show each one of them will have like their electrons around that. And these metals are just placed right next to each other. There's no transfer or sharing of electrons. It's right adjacent to each other. So this is HCl. So this could be copper and maybe iron right next to each other. They're just placed right next to each other. So let's look at let's first look at ionic bonds and how they're formed. So as I said, ionic bonds are going to be formed when we have a metal, so let's say we have lithium. So lithium, if I were to represent lithium, it has one valence electron because it's in group 1 here. So lithium is here with one valence electron. So you can show it as lithium with one electron. Now, in order for lithium to complete its octet, he will require 7 more electrons to become neon. If he has to go all the way to neon, it means that lithium needs 7 more electrons. And remember how we talked about how difficult it is to get even 1 electron, let alone 7 electrons. So which is the reason why if he wants to become a noble gas, then he will probably go back to the previous row by giving off this one extra electron. So lithium has 3 protons and 3 electrons in the atomic state. Now when he gives off that one electron here, now he will end up forming 3 protons with 2 electrons, meaning you have one extra positive charge. So this becomes a positively charged ion, which is a cation. Now if there comes a fluorine atom, now the fluorine atom, if you look at fluorine is in 7th group, 7A group. So which means fluorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. So in order for fluorine to get to neon, he only needs 1 electron. So if this lithium is giving away the electron, then fluorine will say, I'm happy to take it. So he will readily accept that. And fluorine now becomes fluorine with 8 electrons around him, with his octet being complete. So he is happy. But nonetheless, because of the fact that he had 9 protons initially and 9 electrons, when he gained the other electron, he has 9 protons but 10 electrons, one extra electron, which makes him negatively charged. So this becomes an anion. So you have a positively charged cation and you have a negatively charged anion. Now these two will be attracted to each other, and that bond is called as the ionic bond. Just take a few seconds or pause the video here, understand this material, and make sure that you're clear about this concept. So if you actually look at lithium fluoride, once you can see that these are forming ionic bonds, they arrange the ions arrange themselves in a specific pattern, and we call this as the lattice structures. So the lattice structure makes the molecule very, very stable because there is that cohesive attractive forces between multiple ions. Each positive ion will interact with multiple negatively charged ions, which makes the whole structure extremely stable and sturdy. The sugar becomes, we call many a time the lattice structure gives rise to this crystalline nature of the salt. So lithium fluoride, you can see that it appears like these crystal structures. No matter how much you powder, it will still feel textured when you touch it with your fingers. It feels that crystalline texture. That's because of the lattice structure for most of these salts. So let's look at another example. This time we will look at a metal like magnesium, who has an atomic number of 12. So let's find the magnesium on the periodic table. You can see I have magnesium right here. This is column number 2, so the number of valence electrons will be 2. And the other one we have here is oxygen with an atomic number of 8. So if you look at this one, oxygen is right here. And the group number here will be 6. So I know that oxygen has 6 valence electrons. So this is 3, 4, 5, 6, 7, right there. So if I represent magnesium right now, if I have to show magnesium, I will show magnesium with 2 electrons right there. And because he is also on the left-hand side of the periodic table, to get to the noble gas right here, argon is going to be very expensive. So he would rather go back to the previous row neon right here. In order to do that, he has to give away these 2 electrons. So once he gives those 2 electrons away, then magnesium will be like, it'll get the same electronic configuration as the neon. So here it had 12 protons and 12 electrons. By giving away 2 electrons, now magnesium has become 2 plus because it lost 2 electrons, and it still has 12 protons but only 10 electrons. So the now difference in the charge becomes the charge on the atom. So this is the ion here. So this is the cation that is formed here. And now if you look at oxygen, oxygen has 6 electrons here, valence electrons. So which means he is more than happy to pick up those 2 electrons from magnesium, and in the process oxygen will end up having 2, 4, 6 and 8 electrons, making him negatively charged. That's because we had 8 protons and 8 electrons here. Now we still have 8 protons but 10 electrons here. So which is why it becomes negatively charged, and these two are attracted. So this is the anion. So this is the ionic bond that is formed here. So you can see that whether you have 1 electron or 2 electrons, you can have like the metal and non-metal interact and form ions, and in the process they also form the ionic bond. Now what if one of them is ready to give 2 electrons but the other non-metal wants to pick up only 1 electron? So here magnesium, we saw that magnesium has 2 valence electrons and he wants to give away both of those 2 electrons. And in the process he'll become Mg2 plus. Now fluorine on the other hand, if you see fluorine wants only 1 electron. So 1 electron will go to this fluorine, and another fluorine will pick up the second electron right here, and that will become fluorine again. So when these two interact, we'll have magnesium, which has got 2 plus, and we'll have one fluorine on one side, the other fluorine on the other side. So fluorine has got 8 electrons right here. So you can show the 8 electrons around each of those fluorines. So at the end of the day, we have to balance the charges. That's it. So if the center has, the metal has 2 plus, then if the non-metal has 1 negative, so we will end up writing this as MgF2 as the molecular formula. So basically, when you look at the periodic table, you can easily come up with the molecular formula based on the charges, and those charges are based on the valence electrons. So these ones can form +1 and +2 charges. This will be +3. Now carbon will be right in the middle, but the ones to the right of carbon wants to pick up the electron. So nitrogen needs 3 electrons, so he can become -3. Oxygen can pick up 2 electrons, so it can become -2. And halogens can become -1 charge because they can pick up 1 electron. So if I were to have lithium with chlorine, so lithium has a +1 charge because it's in group 1. Chlorine has -1 charge, so together we can make it as lithium chloride. Now if I were to have lithium interact with oxygen, so oxygen is right here and lithium is +1, oxygen is -2. So when we want to make a compound with lithium and oxygen, that means we need to have 2 lithiums for every 1 oxygen that way. So if I were to say lithium, 2 of lithium and 1 of oxygen, that becomes the lithium oxide compound. So essentially what we are doing here is we are swapping these numbers to each other. So lithium becomes 2, oxygen becomes 1. Go ahead and let me know what would be the charges on sodium and sulfur. So sodium has a +1 charge, sulfur has a -2 charge. So when you come up with a formula, this will be Na2S, right? So it's a good practice. So come up with 2 or 3 of these, like, pick one from the metal side, one from the non-metal, and see if you can come up with the molecular formula based on the charges. So you can also use this table here, which gives us all these charges. So group 1 will always have +1 charge, group 2 will have +2 charge, and these are the most reactive ones, the common ones that I have highlighted here. And all of these are going to be metals. And the yellow ones here, these are going to be the non-metals. So metals will become positively charged, positive cations, and non-metals will gain electron and become negatively charged anions. And these two bond together through ionic bond. So this is like, one type of bonding, ionic bonding. Now what happens if we only have nonmetals? Hydrogen is also a nonmetal here. That's an exception. So let's say we have 2 hydrogen atoms interacting with each other. So then it becomes, if you have nonmetal and a nonmetal, it becomes covalent. We'll talk about this one. But before that, let's look at why these ions are important, especially in a biological setting. So we have these ions, sodium, potassium, and chloride. These are present in significant concentration compared to any other ion in the body. So sodium and potassium, as we had discussed previously, they're important for maintaining the electrical conduction. Electrical impulses are being like the neurons, the way the neurons transmit signals is using the sodium potassium charges. And chlorine is also important because it maintains the charge balance across the plasma membrane. And these ionic forms of these elements are also important because they are used in order to maintain the fluids at a particular osmotic concentration or even pH. All of that is based on these like charges, and especially sodium, potassium, and chlorine, along with the bicarbonates, become very integral for maintaining the blood pH. So which is why you can see that many a time we have these supplements. People take magnesium supplements, which are important for metabolic reactions. The ATP molecules, the enzyme that makes ATP or converts ADP to ATP uses magnesium. So magnesium supplements will definitely help in metabolism if there is a deficiency. Zinc is also important for many proteins, and calcium, of course, is useful for bones. So far we talked about predominantly the monoatomic ions, meaning iodine minus or sodium plus and things like that. We also have a few polyatomic ions, and some of these I would like you to memorize. I will hand out these 10 polyatomic ions which you need to memorize. These will be expected for your exams as well as in class activities. So out of the many polyatomic ions, these are the most important ones, and it's something that will be very useful for you even down the line. So phosphate, this is found in many like ATP or ADP phosphate groups. So it has a -3 charge. Sulfate has a -2. Carbonate has a -2. Chromate, dichromate, both of them have -2 again. So these are all the important ones in the -2 category. And in the -1, we have the nitrate, chlorate, acetate, and the hydroxide here. Ammonium is the only one here that you will see with a +1 charge. Even though ammonium, it contains nonmetals, because it has a +1 charge, whenever you have ammonium compounds, they will generally be salts. They will have ionic bonds between the positively charged ammonium ion and a negatively charged anion. So let's say, for example, we are asked to write down what would be the molecular when magnesium interacts with, say, phosphate. So what would be the formula for magnesium phosphate? These are all nonmetals here anyway, so these are negatively charged. So magnesium is going to have a +2 charge, and phosphate group has a -3 charge. So when you want to make a compound, so you need to make sure that the charges are neutralized. So the simplest way to figure out how to balance these charges is to swap these numbers there. So the phosphate is one group here. So this will end up forming Mg3PO4 twice. So if I were to ask you to write down the formula for magnesium and sulfate, so magnesium has a +2 or 2+ charge, and sulfate has a -2 or 2- charge. So because it is 1:1, the formula will be MgSO4 here. So go ahead and try what would be the for magnesium hydroxide. Magnesium has a 2+, hydroxide has a 1-. So when you swap the two, this will become MgOH twice. Now this, whenever you have a polyatomic ion, make sure that you consider the entire set as one group of like set ion right there. So as I said, there is a clear demarcation between metals and nonmetals. So if you have a metal and a nonmetal interacting with each other, then we end up with an ionic bond. Whereas if you have two nonmetals interacting with each other, a nonmetal plus another nonmetal, then it becomes a covalent bond. So if you were to look at two oxygen atoms or two hydrogen atoms, so if you have all of these ones are nonmetals, the hydrogen is also part of this nonmetal category. So if hydrogen interacts with carbon, nitrogen, oxygen, then it's going to be through a covalent bond. Or if nitrogen interacts with another nitrogen to form nitrogen molecule, that's a covalent bond. Oxygen with another oxygen is also a covalent bond. So the way the covalent bonds are formed are because of sharing of electrons. These are covalent bonds. Unlike the ionic bonds, covalent bonds are formed because of sharing of electrons. So if you look at hydrogen, each hydrogen has one electron, but if they were to share both the electrons, they're like, not the octet, but the helium, both of them will get the helium's electronic configuration, noble gas configuration, so they're going to be very stable. So which is why you will never see hydrogen as hydrogen atoms in nature. You will always see hydrogen as hydrogen molecules, the diatomic molecule. If I were to look at two oxygen atoms, so each oxygen atom has 6 electrons. But if they were to share 2 of those electrons, then each of them can claim to have their octet complete. So you can see that we have one pair here and another pair here, which is why we end up forming a double bond with the two oxygens. Previously, when you had hydrogen, there is only one pair of electrons shared. So each bond is one pair of electrons. When the atoms share two pairs, that means they have a double bond here. We can also, those were elements, but if you look at compounds, we can have two hydrogens interact with oxygen such that each of their electronic configuration will match their corresponding noble gas. So for example, if oxygen has 4 valence electrons here, that is shown, and they can share one pair, with the hydrogens. So total oxygen has 6 electrons, valence electrons. That's what is shown here. So in order for oxygen's valency to be complete, oxygen needs 2 more electrons. So it will share the hydrogen's electron. So thereby, you can see that oxygen's octet of 8 electrons is complete. Each of the hydrogens, doublet is also complete. 2 electrons here, 2 electrons here. So this is why water becomes a very stable water molecule. So basically, when we show this one, we have hydrogen bonded to 2 oxygens like that. So this is to show that each of those pairs of electrons are shared between those respective atoms involved in the bond. So just to summarize, we have 3 types of bonds. Ionic bond. Ionic bond is formed when there is transfer of electron. There is a metal that loses an electron to a non-metal and they form an ionic bond. And you can have either charges of +1 interacting with -1, or you can have +2 interacting with -2, or even +1 interacting with 2 minus, wherein the ratio changes. The covalent bonds are formed when there is sharing of electrons. Neither of them is ready to give or take, but they are ready to share those electrons. And each pair of electrons that is shared between a pair of atoms end up forming a bond. If they share 2 pairs, then there will be a double bond. If they share 3 pairs, then that will be a triple bond. So sharing of electrons is usually between non-metal and a non-metal, and we can have multiple non-metal atoms interacting with each other to form compounds. And we also looked at metallic bonds, where you have a metal atom interact with another metal atom, or the similar atom in this case. And this will just there's no sharing or transfer of electrons, but the electrons will remain on the exterior, so they can move between these metal atoms. So we'll continue with this topic and get into we'll talk more about the covalent bonding, types of covalent bonding, and intermolecular forces on Thursday. So feel free to write down if you have any questions, come by my office hours, email me if you need any appointments, or we can work through Google Meet as well. Hope you have a nice rest of the day. I'll see you on Thursday.